We'll see. I think it won't be too bad. Make sure you get the quiz turned in at some point by the end of today. Ideally by the end of lecture, so you don't have to kind of track me down in lab. What we're going to do is... I have lab today.
Really?
Yeah, I've got lab Tuesday, Wednesday, Thursday.
Oh, for organic?
Yeah.
Oh.
Sort of back on topic. What we'll do is finish up Chapter 8, just kind of give you some summary slides. The homework in theory is due Thursday. I'm going to switch that up just so you guys know. I'm not going to make you do homework every week. But instead, you get a quiz. So you'll get a quiz pretty much every week. So we'll go ahead and get that started passing around as well.
Are those more points, or those just the same points that we were originally going to get? From who? Because the point structure from the beginning of the semester.
So the point structure said quizzes were worth, I think, 5 points, and you're supposed to have 50 points worth of quizzes. So we will probably end up hitting somewhere around 10 or 11 quizzes. And what I will do is give you your highest quiz scores, your 10 best quiz scores for your final quiz grade. Does that make sense?
Yeah, I was just hoping for a little extra.
Is that quiz more old material or is it new stuff that we're having?
It's both. It's both pieces. So you'll get pretty much, I think, Chapter 7 questions from your exam, and then some new questions as well. Okay. So as far as Chapter 8 goes, what the heck? Why the slide disappeared? So this may look extremely confusing, and at first blush it probably is extremely confusing. But the idea is that we're starting with the alcohol in the middle. So this is our reactant, and we're going to react that with a variety of different things. Okay, so the idea is that we can put all of this information on a single slide or a single image so that you can make reference to it later on. Okay, I didn't directly talk about this one, so I won't test you on it. But sodium metal acts as a base. It'll give up electrons. Don't have to stress too much about it again. Acts as a base, and it will pull off the hydrogen, and you'd be left with the conjugate base. Okay? As far as all of those other reagents, if we go ahead and take a look at the next one going counterclockwise. Okay, E standing for elimination. So if we add sulfuric acid, a strong acid, to our alcohol, the alcohol gets protonated, typically with a little bit of heat. We can end up with our elimination product. So we end up with our double bond, which is what's shown at the end, okay, with our product. Okay. We can continue to move around it looking at each of the individual reactions. If we take a look at the next reagent, we're looking at hydrogen ion being added with some kind of a nucleophile. And if we add that in an SN1 type reaction, if we look at our products, you'll notice that we ended up with two... Oh,
sorry.
Stalking me around the room. We end up with two possible products. Okay. How do we know we have two possible products? Well, one thing, it says and. Okay. Why are we getting two products? What's the relationship between those two products? Yeah, it's coming back to stereochemistry. These two would be enantiomers, though poorly labeled enantiomers. Okay. Why do we get enantiomers? Because it's an SN1 mechanism that in theory started with chirality. Okay? So one of the results of the SN1 mechanism was the loss of stereochemistry, or the loss of our chiral atom. Okay? We don't really officially lose it, we just lose the optical activity of our reaction. Okay? We continue further around, you get the SN2 reaction. Again, we have to have that hydrogen ion to activate our alcohol, and then X would be whatever our nucleophile is going to be. Okay? And we end up with, notice, inversion in our product. Okay? We've got dashes instead of a wedge on our group. Okay? The last things that we finished up on Chapter 8 was that Thursday. So we looked at SOCl2, and then we looked at our chromic acid species. Okay? Your SOCl2 just does a substitution. One thing that I've added on here, which I probably won't test on, is you'll notice that we get retention of stereochemistry. It started as a wedge in our alcohol starting material, and we ended with a wedge with our chloride. Okay? So if you have stereochemistry, that's something that's kind of important to include when you're drawing up your final product. So your textbook might make reference to that stereochemistry showing up. Okay? Be aware of it. I probably won't test you on it. The next portion, which is why we've got these nice darkened lines, is looking at the redox chemistry, or ultimately all we looked at so far has been oxidation. Okay? And I kind of divided those because to me, I don't expect as much information from you as far as the mechanisms go for those. I do expect you to be able to predict those products. So again, if we start with that alcohol, and we use chromic acid, so H2CrO3, which I keep abbreviating, you might see that as H2CrO4, K2Cr2O7, H2SO4, and heat. Okay, all of those long strings of letters are all ultimately looking at the same reagent. We're looking at something that is a very strong oxidizing agent, and it will fully oxidize our alcohol. So when we're looking at the oxidation reactions, we're looking at adding an oxygen bond. So if you look, we've got an extra oxygen bond from what we started with, and if you go back to that carbon and our starting material, there's a hydrogen there, okay, our fourth bond. Do we have that hydrogen in our product? No. So when we do our oxidation reactions, we're losing a hydrogen atom and we're gaining an oxygen bond. Okay? So in the case of a secondary alcohol, as this one is sort of depicted to be, you'll stop at the ketone with chromic acid as your oxidizing agent. Okay? If you start with PCC, okay, this is where we talked about looking at politically correct chromic acid. It's a milder oxidizing agent, so it's not going to fully oxidize. Okay? And by fully oxidize, I mean it will stop at the carbonyl. So we can get ketones, we could also get aldehydes. Okay? Not all that information fits on there, so there's a secondary thing we could look at. If we looked at chromic acid's oxidizing ability, so here I've listed out a whole bunch of other options for what chromic acid could show up as. Okay, we got all of those reagents. And I'm trying to show this as generically as possible. So we've got our alcohol again, except now it's connected out to R groups. Depending on what those R groups are, we get different results. So if we look to our first example, one of those R's is a carbon, which means what kind of an alcohol do we have? We have a primary. So we could go through and label this as primary, or the one with the 0, right? If we have a primary alcohol, chromic acid will fully oxidize to the carboxylic acid. There are 2 hydrogens to remove. So it will convert both of those into oxygen bonds. Where are those bonds? You get 1 in your carbonyl and technically 1 for that oxygen as well. Okay? If we move to where, too many adjectives or whatever there are in that statement. If we look to the next example, if we make 2 of those R groups carbons, what kind of an alcohol do we have? We now have a secondary alcohol, or 2 with our little circle. Okay, in that case, we only have 1 hydrogen to remove. We only add 1 more oxygen bond, and we end up with our carbonyl. Okay, if we make all of our R groups carbons, what kind of alcohol do we have? We now have tertiary. Let's try that again. Tertiary. If we have a tertiary alcohol, we do not have any hydrogens, which means, do we add any oxygen bonds? No. So if you were asked to draw out whatever was at the end of that reaction, you'd end up drawing your starting material. Or you could specify no reaction. Both of those would be possible answers. Okay? Kind of makes sense? So these 2 slides summarize pretty much everything that you will see in Chapter 8, or everything you've now seen in Chapter 8-ish. Okay, so far. I'll go back to that in a second too. Okay? So this is the material that I expect you to have picked up from Chapter 8. We will come back to Chapter 8 after we look at some alkenes, which is what we're going to be looking at today. As far as what level of depth we're going to look at are alkenes, we're going to go all the way back to chapter 4. Since we've now moved all the way up through chapter 8 and chapter 10. We're now going to go back to the fundamentals that we would have expected from our earlier chapters. Okay? So it's going to become easier at first. It's probably just going to be today's lecture because I don't think I can talk for more than 2 lectures worth on chapter 4. Okay? So on Thursday, we'll end up moving into chapter 5. Okay? So as far as chapter 4 goes, we're looking at the alkene functional group. What does an alkene look like? Or another name for an alkene? Whoops, let's try that again. We're looking at, come on, try that again. We're looking at a double bond. Okay, so if we were going to draw that out, carbon, 2 bonds, right? What?
It's like a second grader drew that. I mean, respect, with all due respect, it was like a second grader.
It is finger painting.
No, not right now. I actually have a pen. It's a pen with a fuzzy tip. Give me a break. Does that look better?
Much better.
Okay. Fine. I'll zoom in next time instead of just scribbling it. Okay? So when we're looking at our alkenes, we're looking at double bonds. So what we're going to go back to is be concerned about our hybridization theory, bond angles, all of that fun stuff from our first exam. Okay? So a lot of your homework questions are going to be going over that. You get your structure, which is ultimately looking at bond angles and hybridization. Nomenclature, so how do you name alkenes? We've already started to play around with naming alkenes a little bit, but we haven't done it officially, so we'll have some now real practice. We're going to go back to cis and trans information, which I kind of skipped over as far as the alkenes. We saw how that applied to cyclostructures, and now we're going to look at it as far as double bonds go. And we'll find out that the cis-trans definition isn't quite good enough, and we're going to convert that into Z and E. Okay? Where Z is ultimately cis, and what? Oh, yeah. I'm not even going to attempt to pronounce it, but yes, you're right. And then E for trans. Okay? The last thing that we'll look at very, very briefly would be terpenes. Those of you in the lab, your limonene lab that we did last week was an example of a terpene. So it's looking at natural products, where those natural products are, what the natural products can do, what they build from. Okay? So let's go all the way back to Lewis structures. I want a Lewis structure for this compound. Where do we start? What about carbon?
Double bond.
I don't want to start there for Lewis structure. You're jumping ahead. Go even further back. Valence electrons. Count your valence electrons. How many valence electrons does carbon come in with? 4. How many carbons are there? 2. Plus the valence electrons that hydrogen brings in. Hydrogen brings in 1. There's 4 of them. What's our total? 12. We have to account for 12 valence electrons in our structure. So what we can now do is start to put together our compound. We'll put our carbons out. We'll scatter our hydrogens symmetrically around. And we'll start to put in our 12 valence electrons. Is that really 12? Yeah, that is 12. Okay. Where should we start putting our electrons first? Okay. We'll put them around our most electronegative elements first, which would be our carbons. Okay, where we'll position them in such a way where we can see them going into the bonds better. So we got 2, 4. So we're starting kind of from our outside, working our way inwards. That gives us 2, 4, 6, 8, 10. We need 2 more electrons. Where should we put those 2 more electrons? Okay. Let's put them on an individual carbon atom first so that we can satisfy our octet. Wherever we have electrons between atoms, we can convert those into bonds. Does this carbon have its octet satisfied? Yes. Does this carbon? No. How do we satisfy it? What we're going to do is share electrons. We'll take the electrons from that one carbon and we'll move them into the double bond. What's the result? So much for an eraser. Okay. Our result is that we now get the double bond, which is where everybody jumped to, which is fine. You're good. You were correct. I didn't ask you to jump, though. Okay. So we now have the basic structure of the alkene. We could go through, and we're going to address this later on when we move into Chapter 5, is that original structure that I drew. Okay. So let's go back to what that was real quickly and just evaluate what's going on with that, because perhaps that can help us understand something about the reactivity that we'll see later. What charge does this carbon have? It's negative. Why is it negative? Has extra electrons. What charge does this carbon have? Positive. Okay, why does that help us figure out our reactivity? What do we have? We have charges. Charges are ultimately a sign of reactivity. Okay? So if we look at an individual double bond, we could say, oh, well, it's neutral, there's no reactivity. It is not super reactive because it doesn't have permanent formal charge. But we can draw a structure that puts that formal charge onto it and allows us to get some idea of the reactivity of our alkene. Okay? So what else can we do with this? Okay, how many electron groups? So now if we jump to our structure, how many electron groups are around a carbon atom? So we've got 1. That's not an eraser. We've got 1, 2, and 3. We'll count the double bond as one group of electrons because it's just 4 electrons in one spot. 3 electron groups. What's the bond angle between the hydrogen, carbon, oops, don't do all that, between our hydrogen and carbons? So what we're looking at for our bond angle is here. That angle we would predict to be 120, because for 3 electron groups, what's the geometry? Trigonal planar. How do you spell trigonal? Not
That's
like
good.
that.
What?
You weren't even here for that. You're not allowed to make reference. Trigonal planar. Okay? So we've got a geometry and we've got our bond angles for all that. That's what I would expect you to be able to predict. We're going to come back to those bond angles in a little bit. What's the hybridization of the carbon atom? sp2. How do we know it's sp2? Well, if we write out sp2, officially we could say s1p2. 1 plus 2 equals 3, which equals number of electron groups. So if we've got 3 electron groups, we're looking for sp2. Okay? So the next part would then be taking a look at this. Sorry, let me go back one more before we turn it into a mess. We said sp2. Okay, if it's sp2, we'll have 3 sp2 hybrid orbitals. What's left over? 1 p orbital is left over. Okay? So we've got our sp2 hybrid orbitals that are along each of those axes, and then we'd have our p orbital. According to how this structure is drawn, where is our p orbital currently positioned? It's in the double bond, true. It's coming in and out of the board. Okay? In and out towards you and away from you. That's where our p orbital is on both of those carbons. So what we can do is attempt to take a look at a figure for this. And if we were going to look at our p orbitals as we've got it drawn, we would see exactly what I've got drawn here with our p orbital information added on there. Okay, that's not particularly easy to see what's going on. So what we're going to do is rotate this structure. Right now, all of the atoms are in the exact same plane, so we don't need to specify any wedges and dashes. It's not technically wrong to specify wedges and dashes when you're looking at double bonds. It's just not necessary. So what we'll do is grab our hydrogen. We're going to pick it up and rotate it upwards. When we do that, we end up with this orientation, or that structure. Okay? Our hydrogens are now coming out at you and away from you into the plane, and what we've got left over is these 2 p orbitals which can now indirectly overlap. We're getting an indirect overlap, which means no longer a sigma bond, but instead a pi bond. Okay, pi bond, or we could even have it as the Greek letters. Okay? So, let's take a look at alkynes. We aren't going to do a whole lot of alkyne chemistry, so we'll keep it a little bit more simple. We can go through and assign this the same way that we did before. Carbon comes in with 4 electrons. There's 2 of them, so we get 8 electrons from carbon. 8 electrons from carbon plus our 2 electrons from our total hydrogens gives us 10 total. We can draw on our carbons, put our hydrogens on either end. I've got 6, so we can do 7, 8, 8, 8, 9, 10. We can draw on where we've got our bonds. Does this carbon have its octet satisfied? Yes. Does this one? No. What do we do? We'll share our electrons inwards. What do we end up generating? We now have our triple bond. Okay? So now what we want to do is evaluate what's happening with that structure. What does that mean about bond angles and all that fun stuff? Okay? So if we've got our Lewis structure, how many electron groups are around an individual carbon? We've got 2 electron groups, which means what about our geometry? We're looking at linear, which is the question I actually wrote up there, 180 degrees for our bond angle. What is the hybridization of a carbon atom? Just sp. Remember, we can go through and put our 1s into that. S1, P1. 1 plus 1 gives you 2, which equals the number of our electron groups. Okay? So we can apply all our hybridization theory. This one gets a lot messier if we look at our orbital theory, but we can go through and do that as well. How many sp hybrid orbitals do we have? We end up with 2, which means what's left over? 2 p orbitals are left over. Okay? So each of those carbons has a p orbital. Where are those p orbitals located? We've got 2 options. Mention the easiest one first, which was in the plane of the paper. So we've got that p orbital. And then Debbie, you mentioned the harder one, which is the one coming in and out of the board. Okay? Doesn't look very pretty, that's why I drew it. So let's move on to the next slide, and there we go. And there it is. Okay? So we've got the p orbital set up on there. Where do we get our bonding? Well, we get our pi orbital overlap there, and we also get one here, which means we end up with 1 sigma bond and 2 pi bonds. Okay? Yes?
So how would you mark that on this test? A pi on the top and a pi on the bottom?
So, no. So that's one of the things that's tricky about looking at these things. So if we go back to the double bond where it's a little bit easier to see that. Oh, that wasn't the double bond. I got to go back further. Okay. If we look at the double bond down there at the bottom, okay, we can't say it's a pi bond at the top and the bottom because the p orbital is both on top and below. Okay. So when we're referring to a pi bond, the orbital overlap is happening between both of those. And if we drew it on like that, that looks an awful lot like a triple bond, which is not what we're trying to say. We're just trying to say that we get 2 p orbitals overlapping. Okay, if we move to the triple bond case, it gets a lot more difficult to represent that overlap. We still get the p orbital overlap, did it again, between that we got before for our double bond. Okay, but we now have a second p orbital overlap. That, not easy to draw. We get the p orbitals in front and the p orbitals technically in back. How would I expect you to draw that on an exam? It's a good question. Probably wouldn't expect you to draw that. Okay? I do expect you to be able to tell me what orbitals are involved in that bond. Okay? So that if we were going to look at all the hybrid orbitals involved, or all the orbitals in that triple bond, what would you tell me? Okay, close.
One S orbital.
So I've got a sigma bond, and then I've got 2 pi bonds. What's in my sigma bond? I have 1 sp orbital, and I have to have another sp orbital. That bond is made up of orbitals coming from 2 carbons. If I looked at the pi bond, what orbitals are involved in that pi bond? P orbital from one, p orbital from the other. How about the other pi bond? P orbital from one, p orbital from the other. The textbook's going to add some extra information to it. I don't care if you add that information as long as you don't add it wrong. Okay? What p orbital are we actually using? Could refer to the carbon p orbital, but as far as atomic orbitals go, we have all sorts of possibilities. We've got anywhere from 2, 3, 4, 5, 6, or 7. Which p orbital are we using? The 2p orbital. Why are we using the 2p orbital? That's our valence shell for carbon. Okay? So we could specify that this is the 2p and the 2p. Okay? Because this is organic chemistry, we're only concerned about those atoms. I'm not going to ask questions where we push into those other energy levels, so that 2 can be implied. Does that make sense? So just so you're aware, you will see that in your textbook. So, and because the textbook addresses this, we're going to look at it a little bit closer too. Okay? We take a look in each of these cases. We've got an sp3 hybridized in the upper case and sp2 in the lower case. What's the bond angle between my hydrogen, carbon, and hydrogen in that structure? It's 109.5. How do we know it's 109.5? sp3 means tetrahedral. Okay, so we're looking at 109.5 degrees. Let's move to the next case. What's the bond angle there? Let's make it easier. What's the bond angle that I expect you to tell me? In this structure, what's the bond angle between the methyl, the carbon, and the hydrogen? It's still sp3, which means it's still a tetrahedral structure, which means it's still 109.5. Okay? Which we would predict out here as well. Okay? The textbook didn't talk about the bond angles changing when we looked at tetrahedrons, but they do for some reason talk about it with sp2s. If we look at an sp2, what's our geometry? We get trigonal planar. What's the bond angle between hydrogen, boron, and hydrogen? Okay, we get 120 degrees. What's the bond angle between hydrogen, carbon, and carbon? Okay, what I would expect you to tell me is 120. Is that what your textbook tells you? No, it tells you it's different. Why is it different? It's related to that. What explains for these bond angles?
You're all pushing each other as far away as they can.
All of those electron groups push away from each other. Why do we get trigonal planar and that 120 degree angle? Because if we evaluate the structure, okay, if we look back down at this guy, all of those bonds are exactly the same. There is no difference between them, which means they're all occupying the exact same amount of space. They're all repelling each other with the exact same force, which means we end up with equal distances between all of those. When we move up into the alkene and we look at that bond angle, are all 3 of those bonds around that carbon exactly the same? No. They have slightly changed, which means what happens? The bond angle, it's also going to slightly change. Okay? As far as what I expect you to be able to do is acknowledge the bulk bond angle. So in the case here, it's 120. How about over here? 120. Okay? Does that make sense? You should be aware of why they're changing, and it's just coming back to where our bond angles came from. Okay? We defined our bond angles because all of our electron groups were exactly the same. As soon as we move to a case where they're no longer the same, much like in the problems up here with our sp3, we end up changing the bond angles. Okay? Along those lines, if we evaluated, say, the reactivity, draw. Which of these two structures is most likely to react or faster to react in an SN2 type reaction? The bromine. Why? Okay, kind of. Bromine is bigger. What happens to this bond length? It gets further apart. So our bromine atom may be larger, but it's now way out here. Which means what happens to our electron density in here? It gets a lot thinner. What do our bonds now down here do? They start to shift to fill that space. What does that mean about the backside of that carbon-bromine bond? It gets bigger. So what we're doing is taking our electron cloud that's, I didn't like the pen anyway, pulling it further away. Our three groups press outwards, exposing the backside of that bond. So what we end up seeing in the SN2 reaction is that this species reacts a little bit faster because the backside of that bond is more exposed because the bromine bond is further away. Okay? Which means we aren't looking at exactly 109 degrees. Okay? Kind of makes sense? So, what do I expect you to know? Your responsibility is ultimately an sp3 hybridized structure gives you 109.5 degrees for your bond angles. sp2, 120, sp, 180. Okay? That's what I want you to be aware of. You should be able to think and reason out why those bond angles will change, but I expect you to tell me that those are the bond angles within there. Okay. So now we can move into alkene nomenclature. You'll notice I've added a whole bunch of words to this one, shrinked fonts, all sorts of fun stuff. Okay? That's because the alkene naming is a little bit more complicated than the other stuff. So let's kind of go through and break this down. You're going to find the longest carbon chain that contains the double bond. It has to have the double bond in it when we're going through and naming our alkenes. Okay? We can then assign our suffix, so that's our meth, eth, prop, but, all that fun stuff. Okay? We'll then number it in such a way that we give the double bond the lowest number. Why the double bond and not our substituents? Because our double bond is typically more important than the rest of our groups. Okay? Because what we typically be looking at least for this chapter, is we're looking at these other things as possible pieces thereof. Okay? We'll then go through and add the "ene" ending. Okay, so we use the "ene" to specify that it's an alkene, our double bond is present. Okay, and then we'll go through and put the number in front of that whole name to establish where the double bond is found. Okay, just like we would with any of the others. Okay, now you can go through, identify all your substituents, put everything together, and you're happy. Okay? If you've got questions about the specifics of that nomenclature system, you should check your textbook. I will try and make sure that the questions I ask are as straightforward as possible, just like for every other exam. Okay? A couple things that you might encounter in the textbook as far as common names go. So that's this little lower corner here. We'll come back to why these are confusing in a second. If we take a look at just a single double bond, okay, between two carbons, the name we come up with is ethylene. Okay, the "ene" ending makes sense because we've got a double bond. Why do we have the YL in there? Because we do. Okay, that's a fair answer. What we're deciding with this name is that the "ene" is our reaction, or our most important thing. Okay? That means the rest of the structure is a substituent on my double bond. How many carbons are in the rest of my structure? 2. So I end up with eth, and since I'm calling them now substituents, I will call it ethyl. So ethylene for the double bond. What happens when we move to the next one? Okay. Again, we're doing the same general idea. We're saying ene is the most important part of my structure. So that's my big piece. What's my substituent? How many carbons do I have? 3, which gives us prop. We're calling it a substituent, so we come up with the YL ending, and we get propylene. Okay? It's the best hand-waving explanation of those common names I can come up with. Okay? And unfortunately, when it comes to common names, there isn't really a nice way to do it. Okay? And then the same kind of idea rolls for that last one. Okay? I don't think I saw any other goofy names, common names floating in the textbook. You got a question about the last one?
Mm-hmm. No,
Okay.
I don't have a question, but I was just thinking that it says butte.
So let's break it again where our line is. Our ene is our most important part. Okay. And what we'll do is now count out all the carbons in our group. 1, 2, 3, 4, which is where we get the bute from. But if it was a straight chain, I could then call it, say, butylene. Is it a straight chain? No. What I have is the iso shape. Okay, that iso shape is this guy here, or some people have referred to it a fishtail. Okay, so I have an iso shape with 4 carbons, so I will call it isobutyl. Okay, with the YL being my substituent name. So it ends up being isobutylene. Okay. One of the reasons we can get away with these common names is it doesn't matter where we put the double bond. Okay? If I'd instead drawn propylene where I put the double bond here. Come on. Why aren't you drawing? I really don't like this pen. If we did our propylene there, that's still going to be propylene. All we've done is just pick the structure up and flipped it over. What if we drawn our isobutylene where our double bond was up at the top? All we've done is just rotated the structure. Okay? So there's no way that we can put the double bond into any of those structures to change the compound. It's still ultimately the exact same thing, which is why we can get away with abbreviating those names in that fashion. Okay? When we move to the alkynes, okay, the ending on the alkyne, this is why I think it gets confusing. The name we end up giving it is the YNE. Why do I think that's confusing? What did we say was our common name endings? There's a Y showing up in there. Oh. Come on. Oh, no, I've got it there. We do have a Y showing up in our common names for the alkenes. Okay? So be aware, just because it's an alkene doesn't mean the Y is not going to show up. Okay? The common name for some alkenes will include a Y as part of the name because we're referring to it as a substituent. It's where we get the ethyl from. Okay? Or the ethyl or the propyl. Okay? As far as the naming goes for your alkynes, very similar to the double bonds, except we'll go through, instead of finding the double bond, we'll find the longest carbon chain that contains our triple bond. Okay? We'll then go through and number it. That was a nice little typo there. Thought I fixed all of those. Wow. I'm going back to finger. Okay. Giving the triple bond our lowest number. We'll change our ending or add our ending onto it to be the YNE ending for the alkyne, our triple bond. Okay. We then go through, put our number through it to specify where it is. You might see that number push around. Some people like to put the number in the middle of the name. That's fine. Or you can put it at the beginning. Okay. Questions about nomenclature when it comes to alkenes and alkynes? Okay. So we'll go ahead and move on. So let's come through some examples. So let's try and break these down. Try talking amongst yourselves first, and then we'll see what we can come up with for names. If you've got questions, just raise your hand. I'll come there and see if I can't help you out. Figure out where to get you started.
The very first one? Okay. Yeah, the longest group. Right. So it'd be like, it'd be that, right? The longest chain? No.
How many carbons are in that ethyl group? 2. And there's 3 in the other, going the other direction, so that'll be your longest chain. So 6 carbons in the main chain, so that's hex. But do we count the ene as a substituent, or do we count that as like...
The ene has to be part of your main chain.
So then we have that, the ethyl as a...
Oh, I get it.
So then it would be more of a... It'd be a pentene, like 2 ethyl, 3 methyl.
When you're naming a pentene,
2 ethyl, 3 methyl pentene.
Mm-hmm. Yes.
on the second one, you have to say 2 pentene, like 2,4-dimethyl 2-pentene?
You have to specify where the double bond is.
But on the first one, because it's on the one, do you have
You
to
don't
still
have to specify it because it's the one.
I still remember that, what Zusamin and Ingadin. Because it sounds cute. Really? No, he's not.
Wait, which one is it?
The second one?
What's wrong with that?
No, it's 1,2-methyl pentane.
Ane?
E. No, but it wouldn't be 1,2. Yeah, 2,4. Where did I get 1,2 from? What is that? What's that little triple bond in the middle? Does that mean there's an extra carbon there, or is that just it's a triple bond?
It's a triple bond.
Okay.
So let's go through and try and break some of these down. So I went through and identified in each of these where the main chain is, and I colored it in red, and then highlighted our substituents in green. Would highly recommend that when you solve these problems that you do something very, very similar. It doesn't have to be different colors, but it helps so that you can go through and identify where each piece is. Remember, as far as the naming goes on these, I'm not super strict on order or how they come apart, but we'll try and be as correct as possible when we name these. So for that first one, how long is our main chain carbon? So we'll have a pent. We have a double bond, which makes the ending ene. Do we have to specify where that double bond shows up?
No, not in this.
Not in this case. It shows up at carbon 1, so it doesn't matter. Our numbering will have to start, however, as 1, 2, 3, 4, 5. We will not number the other direction, because if we numbered the other direction, we'd put our double bond at a higher number. We want the lowest number for our double bond. Okay? So because it's a possible, we'll go ahead and include the 1 pent in front of it. Anywhere that you have a number letter transition, you'll use a dash. What are the substituents? So I heard an ethyl, so we can go ahead and write ethyl for our substituent here. What's the other one?
Methyl.
Methyl. So we've got that one. How do we decide meth, eth, all that fun stuff? We just identify the number of carbons, jump into the next point, deciding where they show up. So what I would also do in the process of naming this is specify the numbers next to each of these as well. So my ethyl shows up at position 2. So I get 2-ethyl. My methyl shows up at position 3. Now that I've got all of my individual pieces, I want to put it together into one official name. Okay? Which substituent should come first? Definitely don't have the space to do this. It goes in alphabetical order, so we'd start with 2-ethyl. We'd include another dash because the next thing showing up would be our 3-methyl, and then we've got our 1-pentene.
What's the 1 for?
The 1 is to specify where the double bond is.
Okay.
Okay, which is not necessary, but it's not going to hurt if you include it there. I think all of the other ones require it, so I figure we might as well include it now. Okay, we move to the next one. What's our longest carbon chain? Well, that's kind of boring, isn't it? So let's skip that one. Okay. Yeah, you're right. Okay, fine. Convinced me. So we're looking at pent because there's 5 carbons. We'll do the ENE ending because it's an alkene. It's no longer at the end of our structure, so we have to specify the number, which means we have to number our chain in a fashion that gives us our lowest number to the alkene, our double bond. Which way do we number it? Top to bottom? Top to bottom or right to left. We'll start 1, 2, 3, 4, 5. If you numbered it the other direction, let's see if I can do it in gray. 1, 2, 3, 4, 5. If we did it in gray, our double bond would show up at position 3, whereas in black it shows up at position 2. So it makes sense to start our numbering in black. We're going to do 2-pentene. We can name our substituents. What are our substituents?
2,4.
We have a methyl. You guys are jumping ahead. Those of you that are too good at nomenclature, stop it. Methyl for each of those. We then need to specify where those methyls show up. The one up here shows up where?
2.
Carbon 2. The one down here shows up at position 4. So we could go through and put our name together and say 2-methyl, 4-methyl, 2-pentene. It's too much of a mouthful, so what we'll do is condense it and say dimethyl, saying that we've got 2 methyls in our structure. We need to still specify where each of those methyls occurred. So if we're going to put our name together, let's see if I can spell backwards and not run into the next one. Nope, I'm going to run into the next one. You guys didn't need that one anymore, right? So I'll keep going. Dimethyl. We need to specify where both those methyls are located. That's going to require a number, so we'll do a dash. We've got one at position 4 and position 2. 2,4 dimethyl 2-pentene. Make sense? Okay, I guess I'll go ahead and do that next one. Which the third one, we're going to go through that one carefully here. The triple bond tends to make a mess of things and make it more difficult. You guys did get that name, right?
Yeah.
Good.
2,3,3 trimethyl 2.
So what we're going to want to go ahead and do is make sure that we can identify where all our carbons are. Okay? So I'll go through and black them in, at least in our main chain. Those are all carbon atoms. So if we go through and count that, we've got 1, 2, 3, 6 carbons. So we're looking at what ending? Hex. We want to change our very end to include that it's a triple bond. How do we specify a triple bond? That's our YNE ending. Where is our triple bond? We'd have to go through and number. We got 1, 2, 3, 4, 5, 6. I unintentionally did this, but it's kind of nice. If we numbered it the other way in gray, 1, 2, 3, 4, 5, 6. Where's our triple bond when we go in the black numbers?
3.
When we go in the gray numbers?
3.
3. There's no difference yet. Okay? So that makes it a little bit more difficult to figure it out. Well, as far as our name goes, regardless, it's going to be 3. Now we can go through and figure out each of our substituents. What are substituents? We're all methyls. So we can go through and then put in our methyls. We now want to decide what those methyls are. Rabble. Where our methyls are located. So we need to specify based on our numbering. Our triple bond didn't help us figure out which way to number. So what we now got to do is go through and decide which of those numberings gives us the lowest number to all of our substituents. Black or gray? Black, because that puts our methyls at positions 2 for each of these and position 5 for that last one. If we numbered it the other direction, we'd have 2 at position 5. We get bigger numbers. Okay? We put our name all together. We're looking at, how do I spell backwards? We've got our methyls. How many methyls were there? 3, which means we're looking for our trimethyl. Where are all of our methyls? 2, 2, 5. I must specify that second 2. Okay? Every single group needs to be numbered on where it's located. Okay, make sense?
Would you deem this if we wrote it out 2-methyl, 2-methyl, 5-methyl?
Good question. No, I wouldn't.
Okay.
I'd accept that. I'd probably cross it out at first and then realize that
Probably
that's
put a
valid.
frowny face,
Yeah, maybe a frowny face.
but full points.
Full points. Okay. Questions about naming those, at least at this point? Those first 3 were all sort of our easier ones. So what we're going to do now is move to what appears to be shorter names, which might be easier to go through and do. We went through and named the one on the left. We're looking at 1, 2, 3, 4, 5 carbons. So it's going to be, God, what's all these pens? We're looking at pentene. Where's our double bond? At position 2. So we've got 2 pentene. What about our structure on the right? Also 2 pentene. Okay, why is this a problem? Are those structures identical? Can I superimpose those 2 structures on top of each other? No. Well, that means they're not identical. If they're not identical, you better give them a different name. Okay? This is where we can introduce our cis and trans terminology. What we'll do is break down, and we're going to look at this again in a little more detail, I hope, on the next few slides. We'll cut our double bond in half perpendicular. Let's pick not green, or not that color, whatever that was. Okay? We'll cut it in half, and then we'll evaluate each of those halves and decide what atoms are attached. So let's take a look at the structure over here. We've got a carbon, and what else is attached to the double bond? There's a hydrogen, an implied hydrogen. Is there a priority difference between carbon and hydrogen? Yes. Which one's higher in priority? Carbon. So let's just star it as saying it's cool. Okay. We'll move to the left side. Same reasoning. Okay, or same logic. We've got our hydrogen versus a carbon. Is there a difference in priority? Which one's higher priority? Carbon, we'll star that. Now what we'll do is cut our double bond in half again, except this time we're going to cut parallel to the double bond. Cut kind of through the middle. And evaluate where my stars are. There's too many colors on that. Get a better color. That didn't work any better. Okay. We'll make it better next time. Let's just say that. Where are the stars? On opposite sides of that line or on the same side? Opposite side, so they would be trans. So we would specify in front trans 2-pentene. If we went through and did that same reasoning on the other double bond, we'd find that our two starred groups, which would be this one and this one, are on which side of the line? Same side, so they are cis. Okay, we'll come back to that too. Okay, kind of makes sense?
How come?
Because our two groups, so if we draw on our other atoms, hydrogens, hydrogen versus carbon, which is higher priority?
Carbon.
Carbon, so we'll star it. Hydrogen versus carbon, which is higher priority.
Carbon.
We'll star it. We cut our structure in half. Where are our stars? Same side of that line or opposite sides?
Same. But do you always make a line that
Yes.
way? Like, how come this one you started this one?
You assign, first you assign sides. We'll look at it where it's a little bit cleaner. It
So
will
you
show
did
up.
that? You
Yeah, I
did
did the exact same
All
thing.
right, because
Yeah.
you just had that line,
Well,
so I was like,
yeah.
what?
So one of the repercussions of your alkenes or alkynes comes back with that p orbital. Okay? So if we looked at our double bond structure, okay, from our standard view, or almost standard view, say in this case, okay, when we looked at it from the side, we could see those p orbitals. What we're trying to decide is, can we convert, so in this case we're in the trans conformation, and can we move to the cis? To do that, I have to rotate around the double bond. So what we're going to do to visualize to see if that's a possibility is we're going to look at that structure from the side, okay, from the end, and what we could look at as a pseudo-Newman projection. Okay, so we're now looking at our carbon in front. Come on, give me red. Is this carbon right here? Okay, with these bonds. To get it to rotate, I'm going to have to rotate this downwards, our hydrogens upwards. What happens to the p orbital? It's also going to have to rotate. Okay? It has to stay perpendicular to the plane of the atoms. So we'd end up at this conformation. We'd have to rotate it once more, and then we could get to the cis conformation. But what happens to the orbital overlap in that middle part? Do those p orbitals overlap anymore? No. Which means we went from a place that was fairly low in energy, where we had those orbitals overlapping, dropping the energy of the structure, to now putting them in a position where they're no longer overlapping. Which means we've drastically increased the energy of the structure. That transition is not easy and does not happen on its own. Okay? Which means what about our ability to convert between our trans and cis? You can't do it. Okay? That has to be catalytically moved. So that's our repercussion when it comes to double bonds. We cannot rotate about the double bond like we could with our single bonds. Which is why we can look at cis and trans conformations in double bonds just like we had cis and trans conformations with ring structures. It's the same general idea. Okay? So, there's our conclusion. No rotation about your pi bonds. Okay? Be it a double bond or a triple bond. We will not rotate around those. So when it comes down to deciding cis and trans, we'll go through and apply these rules. Let me check really quickly here. Yeah. Okay, we can look at adding the cis and trans term to our nomenclature. So we came up with trans 2-pentene and cis 2-pentene. Okay, your trans is your groups, or your higher priority groups are on opposite sides of the double bond, and then your cis is on the same side. Okay? The main reason we look at cis and trans is to identify the relationship between any two groups. Okay, so it really only works when we're looking at two groups. Okay? And we could go through, if we really, really wanted to, and ask ourselves, what's the relationship between, say, the hydrogen and this ethyl? Are they on the same side of the double bond or on opposite sides? Same side, so we could call them cis. Why do we typically not look at that? hydrogens are kind of irrelevant. Remember, one of our first rules was to imply hydrogens. So we don't typically look at hydrogens as our groups. We're really only going to be referring to the relationship of things that are not hydrogen. Okay? So we can apply these rules in nomenclature. We're looking at our non-hydrogen groups, and we'll go through and assign them based on priority. Okay? Which one has the highest atomic number? So let's go through a couple examples here. Ow, hand is totally cramping. So here are the rules that we just talked about. You're cutting the double bond perpendicular. Then you'll star your highest priority in each half. And then we'll cut the double bond parallel to the double bond. And then we'll decide, are our stars on the same side or opposite sides? And we can do that with each of these. So let's go through and look at this first case. I don't know what color I got. So let's go perpendicular first. Let's compare carbon to hydrogen. Carbon has a higher priority, higher atomic number, so we can star that side. Let's move to the other side. Hydrogen versus hydrogen. They're the same. Can we star anything? No. So can we look at cis and trans? No. So this structure we could name without the cis and trans name. We don't have to continue on to step 2. Okay, let's move to this guy here, second one down from it. We'll cut our line in our double bond in half perpendicular first, and then try and decide priorities. Okay, we've got a carbon versus hydrogen. Remember, that is still implied out there. Which one takes priority? So we can star it. If we move to the other side, we've got hydrogen versus carbon. Which one takes priority? Carbon. We can star that. Step 2 is to go through and cut the double bond parallel. So we'll cut through here. Where are our stars? Opposite sides. We would refer to this one as trans. Okay. I'm going to do, which one do I want to do? Do the one right next to it? Okay. We'll do the same idea. Cut it in half. Carbon versus hydrogen. Is there a difference? Carbon is a higher atomic number. That's our important one. Move to the other half. CH3 versus? Is there a difference? No. Can we star? No. Do we have cis and trans? No. What if instead of that being 2 methyls, I made this an ethyl, so I added an extra carbon there. Carbon versus carbon, is there a difference? No. What do we do when we typically don't find a difference? Move 1 atom further away. We can go out to 3 hydrogens on this guy. We can go out to 2 hydrogens here and a carbon. Carbon versus hydrogen, which one's higher priority? Carbon. This one takes precedence, which means this one takes precedence. We have our stars. Cut our double bond parallel. Where are our stars? Same side, we're looking at cis. Okay? So you won't see cis-trans isomerism, which is what they're referring to, is do you have the possibility for both cis and trans conformations? If you have a terminal double bond, that double bond is at the very end of a chain, because what are you going to end up with? You're going to end up with 2 hydrogens at the end. Okay, so you can't have cis-trans isomerism there. Okay? If you end up with lots of symmetry in your structure, which is what we ended up with in this case, okay, before we did our cis, okay, that one is internal, but our 2 groups are the same. So we couldn't star that one either. So that one also does not have cis-trans isomerism. How about when we move to this guy? So if we cut it perpendicular, we look at each half. We've got a hydrogen out here versus carbon. Is there a difference in atomic number? Yes. Carbon will get starred. Let's look at our other direction. Hydrogen versus carbon. Carbon gets starred. We cut our double bond parallel. Where are our stars? Same side, so they'd be cis. Do we have to be concerned about the trans conformation?
No.
The ring structure prevents the trans conformation from being possible. So if you have anything less than 8 carbons, it by definition will be a cis conformation. You will still lose, or you do not have cis-trans isomerization in ring structures. Okay, you can't do it unless you exceed 8 or more carbons. It's the only time you can allow for that to happen.
So if you have like 2 rings attached to each other.
No, like 8 carbons. That one could be trans. I'm not going to attempt to draw that. Check your book. Okay, the last thing that I want to look at would be what's happening in this very last case. Let's go ahead and just erase everything. Okay, we've got multiple double bonds, which means we're going to have to assign multiple cis and trans, okay, when we go through and do this. Okay, taking a step further, if we take a look at, let's start with this double bond here. How many non-hydrogen groups are attached to that double bond? 4. There's 1, 2, 3, 4. Cis and trans only evaluated the relationship between 2 groups. As soon as we exceed 2 non-hydrogen groups, we have to change our nomenclature system, and that's where it moves to E and Z. E and Z are more specific than the cis and trans nomenclature, but they're treated everything the exact same. They'll follow the exact same rules. So if we go through and look at this one, let's kind of assign it first based on what we would say for cis and trans. If we break this in half, bromine versus carbon. Which one has the higher atomic number? Bromine, so we can star that. Carbon versus carbon. Nope, so we move further away. Carbon versus carbon. Nope, so we can move further away. Carbon versus hydrogen. Carbon, this one takes priority. That one takes priority for multiple reasons, not just because it has
Priority because of that double bond.
the double bond, just like we did back with the R and S nomenclature. It's the exact same priority rules, all based on atomic number. If you run into multiple bonds or double bonds like we've got here, that's where you'll have to go through that phantom carbon rule, and we could have found our difference earlier. Okay? We now cut our double bond parallel. Our stars on opposite sides are the same side. They're opposite sides, so we could run with trans, but we said we don't like that term anymore. And it becomes E. Okay? E, go ahead and say it really loud for everybody. Because I can't say it.
Enkigen?
There you go. Enkigen. It's German, whatever it is. Meaning opposite. So there you go. We would refer to this one as the E conformation.
The way that I memorized them.
Okay. If they were cis, they end up getting called C. Trans equals E. Cis equals Z. The only way that I really remember the Z between those differences, or the difference between those two, is that for some reason I can remember cis and trans just fine. Z and E I always get backwards. For Z, think on the same side. Okay, as dumb as that may sound. Okay?
How did you forget that now?
Oh, it's long.
Yeah, good. So Z is cis, E is trans.
I memorized them from
Okay?
tranny and sissy.
I like that.
I'm not repeating that one. So our new rules that we just addressed, your cyclic structures, we've got up here, they cannot be trans if, then 7 carbons. Could have sworn it was 8. Check your textbook on that one. I'll talk about it in class next week, but I thought it was 8 carbons. But I could be wrong. Maybe it's 7 and fewer. Cannot be trans. Okay? If you have more than 2 non-hydrogen groups, you need to be using the E and Z nomenclature, not the cis and trans. Okay? It's ultimately the same thing. If you want to start with E and Z and stick with E and Z throughout everything, that's fine. Go ahead and do that. E and Z will technically only apply to double bonds. It does not apply to rings. Okay? So E and Z, if you're going to name things based on that nomenclature, it's double bonds. Rings get cis and trans with substituents, right? Okay?
So if you find out, like you did one on that last one, and that was trans, so you don't have to do the other one?
So back on this one, if we had to go through and name that, so we went through and decided that this was starred, that this double bond was trans, which we said was E. We would have to specify where that double bond showed up, which in this case, that's all sorts of nomenclature. Let's just say it's at position 2. You'd say 2E way out in front of the name, just like you did with R and S. You'd also have to go through and assign around this one. So if we assigned around that one, do it in a slightly different color. We cut it in half, perpendicular first, hydrogen versus carbon, which takes priority, carbon, hydrogen versus carbon, which takes priority, carbon, cut it parallel. Where are those two? Same side. We would refer to that one as Z. That position, if we followed the numbering that I already set up, 1, 2, 3, 4, we'd have 4Z. So we'd say 2E, 4Z, and then we'd list the name out, whatever it was. Okay?
So that goes, the 2E and the 4Z would
Should be out in front, all the way out front. Yeah. I don't think it's technically wrong if you shift it into the middle, closer to where you name it, but I've always seen it out front.
And a structure that has two double bonds like that, is it like dihexene or?
If we have 2 methyl groups, how would we number those or refer to those in our name? Dimethyl. If we have 3 methyl groups, trimethyl. If we have 2 double bonds, diene. So you have to change, you'll change your prefix on it for the ene part. So in this case, we have, how many carbons? We got 1, 2, 3, 4, 5, 6. We'd have hex for the 6 carbons. There's 2 double bonds, so it would have to become hex diene, because we have 2 double bonds within that structure.
Do you have to say 4Z, 2E, 4, 2 hexadiene, or do you say 4Z,
Yeah.
2E, hexadiene?
Because all the other substituents are going to get in the way, yeah, specify them at the front. If you want to specify them in the middle, that's one of those I could care less things. That's fine with me. That is officially lecture, so we'll go ahead and stop. I will try and